video is on section 14.5, which is on conservative forces and potential energy. There are no example problems for this section, and some of the material I touched on in the introduction video to chapter 14. They start off in this chapter defining what a conservative force is, and the definition that they give you is if the work of a force is independent of the path and depends only on the force's initial and final positions on the path, then we can classify this force as a conservative force. And then examples of a conservative force are the weight of the particle and the force developed by a spring. And if a force is conservative, it has an associated potential energy, which is why we have a gravitational potential energy and elastic potential energy, because those are conservative forces. Now, I'm going to share something with you from Introduction to Electrodynamics by David J. Griffiths, and if you took Physics 261 with me, you may remember that I use this book sometimes in Physics 261 also. So here in this figure we have point A and we have point B, and we can take path 1 to get from A to B, or we can take path 2 to get from A to B. And it doesn't matter what path we take if the force is conservative. But if that is true, it is also true that if we go from point B back to point A, so if we go from A to B and then back from B to A, we started at A and our final position is at A also, then the total work done in that case is 0. And that's how, well, that's what I talked about in the introduction to this chapter. If you have a conservative force and your initial position and your final position are the same, if the force is conservative, then the total work done in that case must be equal to 0. Okay, and then before we move on to the next page, one thing I want to say is that we have this line here, which is the datum, and that is when the gravitational potential energy is equal to 0. So in previous problems, when I said H is equal to 0, that was on the datum. So now we're going to skip these pages because we already talked about them. So now we're going to move down to equation 1419, where they say the force F is equal to the negative gradient of V, where this is potential energy. There's a video that I have for Physics 261, and it might be helpful for you to watch this video if you didn't take Physics 261 with me, because I talk about, in that video, the relationship between a force and a field and a potential and potential energy. However, if you do choose to watch that video now, it may be very confusing to you because here we're using V for potential energy, but in that video we're using V for potential and U for potential energy, and it's kind of hard to keep those quantities straight to begin with because one is potential and one is potential energy. So the names are even similar, there's just, you have to make sure you say potential energy if it's potential energy. Now, I'll be very proud of you if you look at this equation here and say, aha, that equation looks very similar to something that we saw in Physics 261, where we have the electric field is the negative gradient of the electric potential. It looks more similar than it should look to equation 1419 because this V is not potential energy. This is potential, and it has units of volts. But in each case, we're taking the gradient of a scalar quantity, and we are getting a vector quantity. And when we did this in Physics 261, we said it seems like there's more information in the electric field than there is in the electric potential, because the potential is just a scalar quantity. So how can you take a scalar quantity and from that get a three-dimensional electric field? Well, because, and I'm going to go back to the Griffiths textbook here, the electric field cannot just be any vector function. It's a very special kind of vector function, one whose curl is always 0. Okay, now, there's a few things we need to talk about before we go any farther. They define del, this vector operator, for you here in the book. And we did see it in Physics 261, but probably only in a lab that we did, and maybe we didn't have to understand it very well in order to do the lab. But this is an operator. It has to act on something. So here it's acting on t, which is a scalar. You can take this operator and act on a scalar. You can also take this and dot it with a vector, or you can cross it with a vector. When you dot it with a vector, it's the divergence, and when you cross it with a vector, it's a curl. And even though we're looking at the gradient here, it's important to understand what the divergence and the curl are, or at least to have an idea of what the divergence and the curl are. I just lost my place in the textbook, so just give me a minute here. Okay, so here where they're talking about the divergence, they give you 3 different fields. This one, I hope, you can look at and say, well, that looks like an electric field. If you have a positive charge here, that's the type of field you would get. And it could even look like a gravitational field too if you're looking at like the whole Earth and the gravitational field from the Earth. Except in that case, the arrows would be pointing inwards instead of outwards. This looks like a gravitational field, but if you're just on the surface of the Earth looking at a gravitational field in a small amount of area where the height isn't changing much compared to the radius of the Earth. And that's the definition for the divergence, which we're not going to worry about right now. On here, we have fields that have non-zero curl. They have the mathematical definition here, but we don't have to worry about the mathematical definition yet. Instead, you can look at what the curl would actually mean physically. So these are vector fields, and you could imagine that your vector field is the surface of a pond, and you're looking at how the water is flowing. So at every point on the pond, there is an associated vector giving you the velocity at that point, which has a magnitude and a direction. And imagine you're standing at the edge of the pond and you float a small paddle wheel, which could be a cork with toothpicks pointing out of it. So you take this cork with toothpicks and you place it in the pond, and if it starts to rotate, then you place it at a point of non-zero curl. So you can see that if you put your paddle wheel right here in the middle of the pond, this would be like a whirlpool in the pond. The water's flowing in a circle. The paddle wheel would turn. Here, the vector field isn't going in a complete circle like it was over here, but if you put your paddle wheel here, because the water is flowing this way on this side of the y-axis and this way on the other side of the y-axis, your paddle wheel would still turn. So these two vector fields have non-zero curl. And then there's something important, which I think I haven't mentioned yet. Maybe I did mention it. This was back when we talked about the electric field can't be just any old vector function. It has to have always a curl of 0. So it's a vector field whose curl is always 0. So for these two vector fields, there would not be an associated scalar potential because the curl is not to 0. Okay, so you couldn't write a similar equation to the two we have here because the curl is not 0. But for these two fields that we have here, if you take your imaginary paddle wheel and you place it in this vector field or in this vector field, your paddle wheel would not rotate. So this would just be like a stream that's flowing everywhere on the surface of the stream. You have a constant non-zero velocity. It's pointing in the same direction everywhere. So your paddle wheel would float away this way, but it wouldn't rotate. And similarly here, your paddle wheel might drift this way, but it's not going to rotate. So, and that would happen no matter where you place your paddle wheel in this vector field or in this vector field. So the curl for this field is always 0. The curl for this field is always 0. We said this looks like an electric field or a gravitational field from a large, massive object. And this looks like the gravitational field near the surface of the Earth. So there should be an associated potential for the electric field and for the gravitational field. And this is where it gets a little bit confusing, because when I talk about the potential for an electric field, that's this potential, not the potential energy. But now in our dynamics textbook, we are talking about a potential for this force, which is the potential energy. And again, if you want to learn more about the relationships between those, you can watch the video for Physics 261, but just a reminder that you have to be very careful to keep the notation straight in your head, because the letters are getting all mixed up when you go back and forth between the two courses. Okay, so I think that's really all that I wanted you to learn from this. So you can go back and read through all of section 14.5, but the main point is, hopefully now you can have a good idea of whether or not a force is conservative, and conservative forces have an associated potential energy. But I'll just remind you once again that you must be careful when you're using this equation here, because this is your potential energy, and here they call this the work done by non-conservative forces. But they say here that the potential is just equal to the gravitational potential plus the elastic potential energy. But that's assuming there are no other conservative forces acting on the object, which is a safe assumption for this course, but not necessarily true in general. That is why I like to write out the work-energy relation this way, where I just say F other to remind myself that it's forces other than the gravitational force and the elastic force or the spring force, but could possibly include other conservative forces. But when I write out the equation this way, I don't really care whether the force is conservative or not, because knowing it's a conservative force is really only useful to me if I also know the associated potential energy. Okay, so that concludes section 14.5. Be sure to read through it on your own, and that brings us to section 14.6. But I already said everything I want to say about section 14.6 back in the introduction to chapter 14. So in the next video, we will jump right into solving example problems in section 14.6.